Okay, welcome back everyone. Good to see you after the break and even before that, after the week of not really classes that we had. Before I continue, does anybody have a question for me? Yep.
When's the midterm grade coming out?
The midterm grade coming out, I'm promised, will be, the Scantron results will be available by Thursday. Yep.
How was your break?
My break was fantastic. I spent my week sitting at my desk, ignoring any emails that arrived, and writing a paper that actually turned out okay. So it was a good week. Yep. No, nobody collected the scientific calculator that was left here. So if it's yours, come and get it. If you think you know who it belongs to, let them know. I'm assuming it's from somebody who wrote the exam here, but that's not clear. Possibly that person ran away and dropped the course immediately and then was taken off the mailing list. So they don't know. They didn't get my notice. So it's still sitting in my office if anyone, not if anyone wants it, but if anyone can find the rightful owner of it. Yep.
When's like assignment 3 coming out?
Assignment 3 is available now.
Oh, yeah. It's actually not bad.
Okay, so today we're going to pick up where we left off now more than 2 weeks ago. And we sort of left off where you had just learned the basics of probability. And I'll remind you of a couple of things. We have this thing called a uniform sample space. So that's a finite set along with a probability function. And the uniform part here means that every element in the sample space has the same probability associated with it. So everything is equally likely, and we've seen examples like rolling a 6-sided die. Each of the outcomes has probability 1/6. Picking a random integer from 1 to 100, each of them has probability 1/100. We'll see that one again today. So we've seen a lot of these things. So probability of any individual any individual outcome is 1 over the size of the space, and the probability of any event is just the size of the event divided by the size of the space. So we'll work a lot with those. They're really nice to work with, precisely because everything we did in the first part of this course really helps us, because what are these probabilities? Well, they're a ratio, the size of one set divided by the size of another set, and we just spent about a month and a half figuring out different techniques for computing the sizes of sets. So uniform probability spaces are nice for that reason, because we already have a lot of tools to work with them. So we'll start today with something. We have sort of two results. They're both surprising, but one of them you've probably seen before, so it may not be that surprising. And it's what's known as the birthday paradox. Okay, so in this room right now, there are, according to my estimate from just before class, about 120 people, which is, of course, is much less than the enrollment in this course, but that's neither here nor there. The important thing for me is that it's less than 365 people. So there's about 120 people in this class, and there are 365 days in a year. So do you think that there are 2 people in this class who have the same birthday? Where birthday means the day of the year, forgetting the actual year that they were born.
Possibly, yes.
Possibly? Probably. This reminds me of my daughter who's in grade 3 they did something like probability, and the answers to the questions are possibly, impossible, probable, likely, not likely. So who thinks it's likely that there's two people who have the same birthday? Who thinks it's extremely likely that there's two people who have the same birthday? Okay. So 120 people, 365 days. The only sort of tool that we've seen to deal with questions like that so far has been the pigeonhole principle. And the pigeonhole principle tells us, well, there must be one day of the year where 120 divided by 365, take the ceiling. There must be one day of the year where at least one person has a birthday on that day. So the pigeonhole principle doesn't tell us anything useful. And indeed, it's quite possible to get a room of 120 people and everybody has a different birthday because there's a lot more than 120 birthdays. There's 365 of them. On the other hand, you were not selected in this room. The selection process that got you in this class, in this room at this time, really had nothing to do with the day of the year that you were born on. So it's more likely that each of your birthdays is actually a randomly chosen day of the year, with each of the days equally likely, in which case what we're interested in thinking about is what's the probability that there are two people in this room with the same birthday. Okay. So let's set that up. There are D, and I'll say D is 365 days in a year. We'll ignore leap years because this is just a model for a class of problems. And D is really a variable here, but 365 for what we're used to for birthdays. And there are N people with birthdays. List the people out in order and call their birthdays B1, B2, B3, up to Bn. And each of these things is just an integer, January 1st up to December 31st. So January 1st is day 1, and December 31st is day 365. And the assumption that we'll work with, probably not actually valid for birthdays, but it's okay. We'll use it as a toy model for now, is that we have a uniform sample space. So that means each person's birthday is equally likely to be any one of the 365 days of the year, and that's true for each one of these things. So we want to use what we know about uniform sample spaces, and of course for computing probabilities in uniform sample spaces, it's really critical that we know the size of the space. So if I have n people, or if you like, I have n integers. Each one is in the range 1 to 365, so a sequence of these n integers. How many different possible sequences are there?
365 to the power.
Yeah. So there's 365 choices for this person's birthday, 365 choices for this person's birthday, 365 for this person's birthday. So that's going to be the number of days in the year to the power n. And for us, in this room, that's 365 to the 120. Just so we have some numbers we could look at here. All right. And I will say, let's say A is the event at least two people have the same birthday. And another way of writing that is that's the same as saying that BI is equal to BJ for some I not equal to J. So one person's birthday is the same as a different person's birthday. All right. And I would like to know what's the probability of A. So it turns out that computing probability of A directly is difficult. And well, there's lots of reasons why, but it's really because I guess there's lots of things to consider. One of the issues is this at least, because you'd have to consider the cases, if you want to split it up into separate cases, well, you'd have to have where there's maybe 2 pairs of people who have the same birthday, or 3 pairs of people who have the same birthday, or even 3 people who share one common birthday, and lots of stuff to worry about there. Do you think that there's an easier related probability that we could compute that might be simpler? Yeah?
There are no people having the same birthday.
Yeah. So let's look at a complement, which if we read it out loud, that would be everybody has a different birthday. Which in terms of these BIs and BJs is something like BI is not equal to BJ for any I not equal to J. So let's think about exactly what this means. So we can all remember this. The size of the event over the size of the space. And we'll put this into familiar terms. I have a set here of people. There's n of them. And I have a set here of birthdays. And there's b of those. And for every person, person 1 has a birthday that's one of these days. And person 2 has a birthday that's one of these days. So there's a function from people, the things in this set, onto the things in this set. That's what we're looking at. And in fact, the size of our outcome space here, what is that in terms of these sets and this function here?
All possible functions.
Yeah. This thing here is the total number of functions from this set of size n onto this set of size d. Now, if I'm looking at this event A bar, which says no 2 people have the same birthday, what kind of function is that going to give me? Yeah. So if no 2 people have the same birthday, then the picture is really going to look like this. Every person over here gets a different birthday on the right-hand side. So this is a one-to-one function. Okay. So size of S is d to the n is equal to number of functions from a set P of size n onto a set, I'll call it D of size D. And this A bar here, the size of that thing is equal to number of one-to-one functions from, let's say, let's call this one P, this one D, from P to D. Okay? So, do we know how to count one-to-one functions? Anybody remember the formula? It's okay if you forget because it'll only take us 2 seconds to re-derive it. How many choices does this first person have for their birthday? 365, or D in the case of a year with D days, because we would like this to work on other planets as well. So this first person has D choices for their birthday, and the second one can pick any of the D minus 1 other days that were not chosen for the first person's birthday. And the third person can pick any of the D minus 2 days that were not chosen by the first two, and so on. And then the last person, that's person number N, can choose D minus N plus 1. So, or if you like, D minus any of the days that, you can pick any day that the N minus 1 people that came before did not pick. And so this is, we have a way to deal with these things. This is D factorial over D minus N factorial. All right, now I think we have everything we need. So we wanted to know probability of A. We couldn't figure that out, so instead we looked at the complementary event, and we figured out the size of that complementary event. So if we know the size of the complementary event, we know its probability, which is the probability of that thing is equal to the size of that thing divided by the size of S, which is D factorial over D minus N factorial divided by the size of S, which is D to the N. But we didn't want to know the probability of this event. We wanted to know the probability of this event. And for that, we use the complement rule. The probability of A is just 1 minus the probability of not A. And if you don't like this, instead you could compute the size of A using the complement rule for computing the sizes of sets. You'll get the same result either way. So the probability of A, which is at least 2 people have the same birthday, is 1 minus D factorial over N minus D factorial over D to the N. Okay? All right. So, is that big or small? No idea. So we can evaluate it because it's, I mean, we have some numbers. And let me give you 2 values of this thing. Here they are. if D is equal to 365 and N is equal to 22, then the probability of A in that case is 0.476. So if this room had only 22 people in it, the probability that 2 of them would have the same birthday is about 47%. And if the room has 23 people in it, then the probability that 2 people have the same birthday is already more than 50%. Yep.
Just for my notes, on the bottom there, if you have n minus d factorial.
Sorry, it should be D minus N. Yeah. There are more days than people, otherwise it doesn't make sense. Good. So already when you have 23 people in a room, the chances are better than 50% that 2 people have the same birthday. And if you go back to, is this really an accurate model of real people? Probably not. Birthdays actually tend to be more clustered around certain days of the year, certain times of the year. September is a very common year for birthdays because it comes 9 months after Christmas break. So in fact, in reality, if you really had the distribution of days of the year on which birthdays are, these numbers are actually higher. Because the less uniform it is, the more likely it is that 2 people end up with the same birthday. And actually for here, in this room, I'm absolutely certain that there's 2 people with the same birthday because at 120, at 120, this number becomes very, very close to 1. So it's almost certain that there's 2 people with the same birthday. So I'm going to put aside for a moment this expression for the birthday paradox, because we might come back to it. And let me state it a slightly different way. Here's the theorem. If we throw n balls uniformly at random into D buckets, a lot of people like to call these bins, in case you end up searching for them, then the probability that at least one bin contains at least 2 balls is 1 minus this d factorial over d minus n factorial d to the d to the n. We'll save that for later because, as you guys noticed, you had no idea whether this thing was close to 1 or close to 0, just even with the values 365 and 23. We'll see a way to tackle those, and we'll see why 23 is magic. But for now, let's move on to our second surprise. Let's consider a game. And here's how the game works. And I'm going to say secretly, pick 2 numbers, 2 integers, x less than y, and each of them is an integer in the range 1 up to 100. And then I secretly do one of these two things. Put X dollars in what I'll call the left box, and Y dollars in the right. Or, clear that I only do one of these two things, or I put Y dollars in the left box and X dollars in the right. Okay? And then finally, I close both boxes. So the picture looks like this. There's a left box and a right box, and maybe the left one has X dollars in it and the right one has Y dollars in it, or maybe it looks like this: Y dollars in the left and X dollars in the right. Now let's see if you've been paying attention. Which would you rather have, X dollars or Y dollars?
Why?
Why? Because I pick two integers, X and Y, dollar amounts between 1 and 100, and X is less than Y. So you would like to have the box, you would like to have Y dollars. So you'd like to have the contents of the box that has Y dollars. Problem is, I did all this in a room that you were not privy to. So here's the game we're going to play, and you don't even know what X and Y are, because I picked those and I didn't tell you. You just know that I followed these rules for some values of X and Y, and that means that one of the boxes has less money in it than the other. So here's what you can do. You open one of the boxes and look inside. You decide to keep it or take the other box. And you win if you take the box with Y dollars. Okay, so let's play this game. Here's what you see. I've made my choices. Which box would you like to open? Doesn't matter, you don't know anything, they're identical. Let's just open the left one. Okay, you open it and you see $50. It's decision time. Do you want to keep the $50 or take what's in the other box? Other box? Okay. So you're throwing this away and opening the other box? You know, some people are shaking their heads. There's a risk here. This box might contain as little as $1. It might contain as much as $100.
As we open that box, all the possibility goes into that box.
So I'll be honest, and I had in mind $60 for this box. So if you switch, you would do better. So you got lucky that time, but you could have got $1 instead of $50. Now, so in this case, if you switched, you win. And that's what it means to win. It means you get the box with more money. That's the definition of winning. So, do you think that there's any, is there a rule, do you think, that could allow you to win with any chance better than just flipping a coin? So can you win this game with probability more than 50% or more than 1/2? Yep.
Is there a way to mathematically figure out what the probability is?
Well, that's what we'll work on. We're going to try and come up with a strategy that lets you win more than half the time. Yep. Yeah.
So there are 49 possible in the first box, so the second one has just a slightly higher probability.
No, because I didn't pick my numbers randomly. So my numbers are just two numbers that I picked. So keep in mind, if I pick the numbers 99 and 100, if you open up the box that has $99 and you decide to keep it, you lost the game. Okay? So you still keep the money, but you lost the game. So it's important the definition of winning is critical here. Okay. Yep.
1 in 100. Or 1 in 99.
So no, there's no probability involved in this yet. I made two choices that I decided to make. They're whatever I could do to make the game maybe as hard for you as possible, and then there's no randomness yet. Yep.
So would it make it possible the probability that you only switch boxes if it's not $100 in the first box? Because it will eliminate the event space where there's not boxes.
If you only switch boxes, if it's not $100 in the first box, then I'll give you lots of things where you'll lose. I mean, there's lots of ways for me to make you lose. Yeah. No, so we shouldn't get confused. I picked two integers, x and y. These are not random. So maybe I will always pick the integers 99 and 100, but you don't know that. Yep.
Maybe there's two independent cases where first you can either pick a greater number or a smaller number.
Okay.
I'm not sure if it's right, and then you multiply it by all possible possibilities.
So this is actually a really tricky one. So first of all, can you guarantee that you win the game 50% of the time? How would you do that?
Random choice.
You flip a coin, take the left box or take the right box. Don't even look in it. Just flip the coin and take it and walk away. Then half the time you will have chosen the box that contains y. Do you believe that? So winning the game 50% of the time is easy. And you better be careful that if you come up with a different strategy, you win at least 50% of the time, which is maybe not so easy. So let's see what a strategy looks like that could get you a little bit more than 50% of the time. And let's make things really easy. Maybe you don't know x and you don't know y. But what if you know z, where x is smaller than z and z is smaller than y? What if I told you that? So I pick my x and y, and then I give you also this value z, and say, let's play the game now. What would your strategy be? Yep. What's that? No, there's still only 2 boxes with X. One has X in it, the other has Y. But I've told you, oh yeah, the number of, one of the boxes contains less than Z dollars and the other one contains more than Z dollars. What's your strategy? Yep.
I open one box, if it's less than Z, then I swap.
Yeah. So there's a 100% guaranteed winning strategy. If I really told you this value Z that's between X and Y, I open the box, I look in and I say, well, there's less than Z dollars in here, so the other one must have more than Z dollars, so I would take it. Or I open the box and I see more than Z dollars in here, in which case I know the other one has less than Z dollars, so I keep this one. So this makes the game too easy. Because it's not the original game. This is the original game. You're not given this Z. But here's something we can do. Let's just pick a random Z. So this is the first time that we're talking about probability here. Everything else about this game was just a mind game with me putting money in boxes that I decided what, I'm trying to play mind games with you. Now you're going to come up with a strategy which uses randomization. We saw one of them is just tossing a coin and choosing based on the result of the coin toss. But here's a different strategy. You're going to pick a random Z and you're going to choose it so that you have some chance of getting this kind of Z, the winning Z. And so that means you're going to pick it and it's going to be either 1/2 or it's going to be 1.5 or it's going to be 2.5 or it's going to be any integer up to 99.5. Okay? So I'm going to pick that Z. I'm going to assume that it satisfies this, and then I'll just follow the rules assuming that. So I open the box, I look inside. Do I see more than Z dollars or less than Z dollars? If I see more, I keep it. If I see less, I switch to the other box. Yep.
So a half because they're X and Y, then you have.
Half just because I want to pick a number that's not going to be equal to X or Y. So instead of picking an even number of dollars, it's some number of dollars and 50 cents.
Why do you have to add by 2?
No adding by 2. This is just, if you like, this is just 0.5, 1.5, 2.5, up to 99.5. Okay. So, first thing, and I'm going to pick this uniformly at random, which means somehow there's some uniform probability space. So what, how big is this set that I'm choosing from? Yep.
Doesn't your Z have to start at 1.5 because your small is also X and Y?
Good point. Let's see. Make sure I didn't make a mistake. Oh, no, I did make a mistake in the definition. It's worse than you imagined. I could even put $0 in the box. So one of the boxes could have nothing in it, for example. The X box could have nothing in it. Good catch. Okay, so let's analyze this thing and see if this gives us a better chance of winning. Seems crazy to think, well, if I had this nice value Z I would be able to win all the time. So instead I'll pick a random Z and hope that it's a nice one and somehow some magic happens and maybe I win more than half the time. So let's see. All right. So let's be really clear. My strategy is pick Z from this set, pick left or right at random, open the box I picked. That's this one, left or right. And see some money. I'll see $A. That's what I'll call whatever's in that box. And if A is less than Z, then take the other box. If A is bigger than Z, then keep this box. Okay? So it's clear what's going to happen. So what's going to happen is some magic is going to happen. So this is a probability question, and this is a class about uniform probability spaces. So we better figure out the set S. What does it look like? Well, there's basically two things, right? I pick this thing here from a set of size 100. These are the two random things. Set of size 100. And then I pick a box left or right from a set of size 2. So that means the total number of ways that I execute this thing, or the total number of choices I have, is 200, right? 100 here times 2 here. So the set S looks like let's say 0.5 up to 99.5 times, and instead of saying I pick left or I pick right, what happens is when I pick that thing, I open it up and I see some money inside the box. And so what I see is either X or Y. I don't know if it's X or Y when I see it, but that's what happens, right? When I open a box, I see X dollars or I see Y dollars. All right. So, let's look at, I want to know the probability of winning. So let's say W is the event. I win the game. And I'll tell you right now, the complement rule is not going to help. What actually is going to help here is the sum rule. And here's the two events that you'll use for the sum rule. Wx is the event. I open the box containing X, and I win. And Wy is the event. I open the box containing y. And I win. Which translates into, I open the box containing x, and for some reason I switch boxes and I take the other one, or I open the box containing y, and for some reason I decide to stay with that box. And we know what that reason is in either case, right? So I open the box containing x and I win. That happens if z is bigger than x, right? If I open the box containing x and the number z that I picked was bigger than x, then I win. If I open the box containing y and the number z that I picked is less than y, then I'll win because I'll stick with this choice. And let's see. Are these disjoint events? Yes. Either I open the box that contains x, or I open the box that contains y. I can't do both of those things. I mean, those are definitely different things, which means these are different subsets of this probability space. Which means that the sum rule applies. So all we need to do to compute the probability of winning is to compute the probability of winning when picking the x box and add that to the probability of winning when picking the y box. Let me clean that up. So these don't bleed together. Okay, good. Let's calculate this one. What is this Wx? Well, Wx are these things where I see an x and I picked some value z, and this value z is smaller than x. So how many z's are there that are smaller than x? So if x is 1, how many of these values are smaller than 1? 1. If x is 3, how many of these values are smaller than 3? 3. So if x is x, how many of these values are smaller than x? X. Okay. So such that z is in 1/2, or let's 0.5, 1.5, all the way up to, this would be x minus 0.5. And we've just decided that actually the size of this set Wx is equal to x. So if there's x dollars in that box, and I open that box with x dollars, then this basically says these are all the ways that I'll win, all the choices of z that allow me to win there. Okay. Let's look at Wy. These are the outcomes where I pick z, I open the box that contains y, and z is in the set. Well, now I need all the values that are bigger than y. So if y is if y is 1, then how many values are bigger than y? 99. And if y is 2, how many are bigger than y? 98. Okay. So this is the z in y plus 0.5 up to 99.5. So the size of wy is, I think we figured out that it's 100 minus y. Right? If y is 1, then there are 99 values here bigger than y. If y is 2, there's 98, and so on. And if y is 100, there's actually 0 values in here that are bigger than y. Okay? Did I get that right? No, I did this exactly the wrong way. Sorry, guys. I win here if I pick x and I change values. Sorry. Let's change this completely around. Okay. Please stop me when I say things that don't make sense. I win here if I pick a value of z that is bigger than x, right? That means the thing that I see is smaller than z, so I'll change values. So this should be x plus a half. This should be x plus 1.5, all the way up to 99.5. And here, I'm happy if I pick a value z, which is smaller than y. So that would be 0.5, 1.5, all the way up to y minus 0.5. Let's get these sizes right. We did them correctly. I mean, we answered them correctly when I defined them. The wrong way, so let's see. For y, this is easy. This is counting up to y from counting up to y minus 1, starting from 0. So there's exactly y of these things. And this one, there are exactly 100 minus x of these things. There are this many choices for z that are bigger than the value x. Okay. So now for sure it's not clear because I've just completely inverted everything, but let's just check. So let's say I put $50 in here, $60 in here, you pick your value z, and you pick the value z is equal to 75.5. And you open up this box. What do? I see something in the box which is smaller than the value z, so I change. So then I take this box. On the other hand, if I pick z as 75.5, and I open up this box, what happens? I look inside, I see a value that is smaller than 75.5. I think I can do better than this, so I change and I lose. Okay. All right. Okay, good. So we've got everything right. Now we just need to know, we know the sizes of these things, which means we know their probabilities. We can finish up. We had the size of S is equal to 200. So probability of Wx is the size of Wx divided by the size of S. The probability of Wy is the size of Wy divided by the size of S. The size of S is 200. The size of Wx is 100 minus x. The size of Wy is y. And what can you tell me about this thing? I can write it another way. It's 100 plus y minus x divided by 200. So this is a half, 100 divided by 200. What about this number? Can you tell me anything about it? It's greater than 0. In fact, it's greater than or equal to 1 because x and y are integers, right? So the boxes have two different amounts and y is larger. So this number here is bigger than or equal to 1. So you get 101 is bigger than or equal to 101 over 200. So even if I play a mind game with you where I put $54 in one box and 55 in the other, you still have a chance, better than 50% chance of winning. Yep.
Where did the 100 come from?
101 is 100 plus y minus x, and y minus x is bigger than or equal to 1, so that means that this is bigger than or equal to 101. Yep.
How do you guarantee that that you pick is between x and y?
You don't. No, I mean, a lot of times you come up with examples like I said, there's $50 in one box, 60 in the other, and you pick some number like 75.5. That's not good if you open this box because then you'll change. On the other hand, that is good if you open this box. So the way to see this is just by proving it, but there's also a sort of intuitive explanation for it, which actually you can really see it from this last inequality where I said that this is bigger than or equal to 101. But actually, the extra 1 here is just the difference between x and y. So really the game looks something like this. You've got a 0, you've got 100. Somewhere along this line, you've got x, and you've got y. And if you happen to pick your z that landed in between x and y, then it doesn't matter which box you open, you're going to win. On the other hand, if you picked your z over here, then you're only going to win if you open the box that said x. So, you have sort of, if you pick your z anywhere over here and you open x, then you'll win. On the other hand, if you pick z somewhere over here, so smaller than y, that pick your z anything smaller than y, then if you open y, you're going to win, right? Because you're smaller than y, so you'll stick with it. So what's really happening is there's this overlap in between where you win no matter what happens. And that overlap is of size at least 1. But in reality, it's actually the further x and y are apart, in fact, the more you care about winning in that case, the better your chances are of winning this way. Okay. Questions? Yep.
Can you explain
size of your sample space there for the grid?
Size of the sample space is, I picked this number, which was from the set 0.5 up to 99.5. So there's 100 numbers in that set. So you're basically counting from 0 to 99. So that's 100 different numbers. And then I flipped a coin to decide whether I was going to open the box that contains X or the box that contains Y. I don't know if I'm opening the box that contains X or Y, but ultimately that's what happens. I open one box or the other. So 100 choices for this first thing and 2 choices for the second thing. So the product rule says that there's 200 possible outcomes. And the number of those that win is 100 plus Y minus X of those 200 that are result in me winning. Yep. There's no randomness in the initial set. So I don't even care about the size of that thing. So the X and Y and which one goes in which box, that's not random at all. That just happens. And once that happens, then this is really the setup, because I flip a coin to decide which box I'm going to open. So I'm equally likely to open the one that contains X and the one that contains Y. And I I pick a random number from this set, so I'm equally likely to pick any of these things. So once X and Y are fixed and they're put in their boxes, then this is the randomization that happens. This is the probability space that we're working in. And the only place where X and Y ever come into it is if you want to know the exact probability of winning, it's actually 100 plus the difference between X and Y, which I can always guarantee is at least 101. 200 is the size of the set S. So that's the number of choices for this number Z that I pick. There's 100 of those plus 2 choices for which box I open. Yep. Yes, this assumes that in the original statement that the number of dollars in the box is between 0 and 100. Integer between 0 and 100. Yeah.
So your winning condition is first you pick the Z that just happened to be between X and Y.
Then for sure you win. Then doesn't matter what box you open.
And on top of that, you pick or if not that, you pick the right box, so that the Z will work in your favor.
Yeah.
Okay, and I guess the product is like the more apart Y and X are, the more winning chance you have.
Yeah, because the further apart they are, the more likely you are to pick Z that's in between
So
them.
if they are adjacent, you just have
If they're adjacent, there's only one number you can pick that's going to guarantee that you win.
But if it's 0 and 100, you're almost guaranteed.
If it's 0 and 100, you are certainly guaranteed. In fact, then this becomes 200 out of 200. Because there's 100 choices for X that are bigger than X, and there's 100 choices for Y that are smaller than Y. 100 things in here are bigger than 0, and 100 things in here are smaller than 100.
Oh, so that's where the 200
Sorry, it's not for X. There's 100. If I open the box that contains X, then 100 choices in here are bigger than the value I see. And if I open the box that contains Y, 100, then 100 choices are smaller than that value. Okay? Okay, so then let's very quickly come back to this thing. This ugly expression here. This birthday paradox expression with this ugly d factorial business in it, and see what we can do about that thing. So let's call this thing we're going to call this P. It's the probability of getting 2 people with the same birthday in this special planet where there's 365 days a year and the population is N. or this planet where there's D days in a year and the population is N. And let's take Q just to be 1 minus P, which means Q is equal to D factorial over D minus N factorial over D to the N. And we'll write that out longhand because it's simpler that way. So here we have D times D minus 1 times D minus 2 times D minus 3, D minus N minus 1 divided by D to the N. Okay? And I'll write that out even slightly differently. So what have I got here? How many factors are there on top? So if I count down, this is like D minus 0, and then counting D minus N minus 1. So that's N things up on top, right? And nice thing is there's also N things down on the bottom here. So let's group those together. So that looks like D over D times D minus 1 over D times D minus 2 over D times D minus 3 over D, and so on down to D minus N minus 1 over D. And these things also can be cleaned up a little bit. D over D for sure has a simpler representation. Anyone? Yep. This is 1. And D minus 1 over D has actually a more complicated representation, but it's useful for us. This is just 1 minus 1 over D, right? There's the 1, but then you've got the minus 1 over D. And this is 1 minus 2 over D. And this is 1 minus 3 over D. And so on, all the way down to 1 minus N minus 1 over D. Let's pause at that. So, go back to a calculus course and remember that there's this magic number E called Euler's constant, and it's involved in lots of neat things, but one of the things you may or may not have seen is that 1 plus x is less than or equal to e to the x for every real number x. Including the negative ones. So that means 1 minus x is less than or equal to e to the minus x. Nothing special there. So you can find this in a calculus textbook, and in most cases or in many cases it doesn't look that useful because if x is big, this is not terribly useful at all, right? If x is really big, this is a negative number, this is a positive number, that's kind of obvious. But actually, when x gets really small, when x gets close to 0, well, this gets close to 1, and this thing's also getting close to 1, and actually these two things get really close together. So there's not much, you're not losing much here. So what have we got here? Well, this looks like what we had there, right? I mean, here we've got 1, which is 1 plus, or 1 minus 0. But here we've got 1 minus 1 over 365. 1 over 365 is a small number. So let's use this inequality on all of these things. So this is less than or equal to e to the 0 times e to the minus 1 over d times e to the minus 2 over d times e to the minus 3 over d all the way up to e to the minus n minus 1 over d. So I have a whole bunch of things, all exponents from the same base, and I'm multiplying them together. What does that do? You add the exponents together. Right? So a to the x times a to the y is actually a to the x plus y. And that's the situation I have here over and over again. So that thing is equal to e to the 0 minus 1 over d minus 2 over d minus 3 over d minus 1 over d. Forget about the dividing by d's. Do you know this sum at all? We've seen that one. 1 plus 2 plus 3 plus 4 plus 5 all the way up to... Yeah. So this is the famous Gauss sum, which if I haven't told you the story already, I maybe will later. But the short version of the story is this is something a 9-year-old can do. So this is 1 plus 2 plus 3 and so on, all the way up to n minus 1. That is n times n minus 1 over 2. But let's not forget that there's a d down here, so this is n times n minus 1 over 2d. Okay. Which is e to the minus n squared minus n over 2d. Negative exponents are confusing, so this is 1 over e to the n squared minus n over 2d. And this is something we can get a handle on now. Why? Because, and why is it showing up? Why is there an n squared showing up here? When is this really big? When is this really small? So this is something that's, this is a base to some exponent. So this is something that if what's up here is big, then this gets really big and the whole ratio gets really small, close to 0. On the other hand, if this is really small, then this is close to 1, so the whole ratio gets close to 1. But the point is that there's an n squared up here. This is the number of people. And on the bottom is the number of days in the year. So, and when this is when this is about 1, then this is like 1 over e. E is 2.7, so this is close to a half. So as soon as the number of people squared gets close to the number of days in the year, this probability of two people having the same birthday already gets quite reasonable. It gets close to a half. And in fact, it's twice the number of days in the year. And so if you think of this example of number of days is 365 and number of people is 23, square 23 and compare that to 2 times 365, that's where this is showing up. Okay. So the birthday paradox basically happens once the number of people is about the square root of the number of days in the year, then you're likely to get people with the same birthday. Before that, more than likely everybody has different birthdays, After that, very quickly, you get people with the same birthday. And this is where we stop because there's a class coming in to write an exam now.